I'm going to start with problem 36 first because this is going to lay down a lot of foundational background to what is going to become pretty redundant. So recall in an ionic compound, one way to characterize those compounds is that they're formed by combining a metal with a nonmetal. And now this is, of course, not an exact strict thing, but generally this is the case. You can also use the difference in electronegativity, as we learned in our last chapter. Generally, if you have a difference in electronegativity of greater than 1.7, or some textbooks use 2.0, then we can classify it as ionic. And the third way we discussed how we can distinguish between ionic and covalent compounds is their properties. And we emphasize that because ionic compounds have that strong attraction, that Coulomb attraction. They have generally high melting points where they're usually crystalline solids at room temperature, whereas covalent compounds, their melting points and boiling points are largely determined by their intermolecular forces, which are much weaker than ionic attraction forces. All right, then you also have the conductivities of electricity when they're molten and when they're dissolved in water. And so these are several ways you can distinguish between the two, but now we're in the topic of how to name these things. And so it's going to be important to distinguish between these to understand why we have these rules in place. So let's take a classic example of a ionic compound where we take sodium metal, with one valence electron. That's the thing we threw in the water and it exploded early in the year. And then we took chlorine gas, and that's the stuff we breathed in our lab. I'm just kidding. We did not do that. Now, this is your metal, and this is your nonmetal. Right? And in an ionic compound, the metal generally loses this electron and forms a cation. And the nonmetal gains electrons and forms negative ions we call anions. And these attractions between those positively and negatively charged, that's your Coulomb attraction. That's your ionic bond. Now, the reason this is important is because these things, they extend in all directions. And you can say practically it's uncountable, although we are going to learn how to count them in our next chapter. But this is why we have to reduce the formulas of ionic compounds. Let's say there's like 13 sodium ions and 13 chloride ions. You wouldn't say that's the formula for sodium chloride, because that's just one little snippet of, this is just a sampling of the real thing can have way more than this. And a larger salt crystal versus a smaller salt crystal doesn't mean they're different things. They're both salt. So that's why we reduce, and then you would get a formula unit. In this case, sodium chloride is Na1Cl1, when we don't write these ones. That's why it's important that's why we have the rule of reducing when we're talking about ionic compounds. Now let's talk about molecular compounds, which are generally made up of nonmetals and nonmetals in what we call covalent bonds, where they share electrons. So a simple case here is like hydrogen. A hydrogen is the nonmetal with one valence electron, and because two hydrogens, if they share a pair of electrons, they achieve the octet, then that hydrogen molecule, now we say, is made up of a discrete number of hydrogen atoms, in this case 2. So when we write the formula, it's H2. Let me give you a different example. This was maybe not the best one. Carbon dioxide is another example. So carbon dioxide, if you draw the Lewis structure, it looks like this. Now, when we write the formula, we know it's CO2. It's not C13O26. That's never the case, because this molecule is a discrete unit of 2 oxygens and 1 carbon. It doesn't have a crystal repeating lattice structure. It has a discrete beginning and a discrete end. This is 1 molecule, but you can't say that about this. All right? So that's the reason, get back to my point, that's the reason we do not reduce. So to answer our original question, an ionic compound is composed of ions in a repeating lattice structure, whereas a molecular compound is composed of molecules, discrete molecules, with exact number of atoms. So now that we got that out of the way, let's start naming and writing formulas for these compounds. All right, write the chemical formula for iron 3 oxide. Now, iron is a transition metal with multiple cation charges. If we're going to write the formula, we have to be given the charge of the cation, and we're going to give that to you in Roman numerals. So in this problem, iron forms a 3 positive cation, and oxide is oxygen, and oxygen formed a 2 negative charge because it gains 2 electrons in its most stable ion. Now we're going to take these numbers and crisscross them to the subscript of the other element, and the formula for iron oxide is Fe2O3. Don't bring the charges down, it's just the numbers, and we got the ratio that way. There's our answer for iron 3 oxide. Number 2, chemical formula for calcium sulfide. Calcium is in group 2, so its most stable ion is going to be from losing 2 electrons. So calcium is going to have a 2 positive charge. You just need to remember all the metals in the second column is going to form 2 positive charges, and sulfide is sulfur. If it ends in IDE, usually that's just the element name. It has to be changed to IDE. So sulfur, because it's in group 16, is going to have a 2 negative charge. Okay. So you won't get this periodic table with the charges on it, but you'll just get a regular periodic table. All right, crisscross these numbers down. Now you'll get Ca2S2. Now this is a metal and a non-metal, so you have to reduce, and your final answer is going to be CaS. Moving on, copper 2 sulfide. Now copper is another transition metal, has multiple charges, so we're going to have to indicate the charge in Roman numerals there for you. The symbol for copper is Cu, and the charge is 2 positive. Sulfide as an ID, that's sulfur, so that's going to have a 2 negative charges in group 16. You're going to crisscross these numbers down. Don't bring the charges down, and you're going to get Cu2S2. Again, this is ionic. We have a metal and a non-metal, so we need to reduce. So your formula unit for copper 2 sulfide is Cus. Now, moving on, potassium nitride. There's another metal and non-metal. We're going to need charges anytime you have that. Potassium is in group 1. It has a 1 positive charge. IDE, nitride, that's nitrogen. That's group 15. It's going to have a 3 negative charge. Crisscross those numbers down to the other side, and you're going to get K3N. You can't reduce that. That's your formula for potassium nitride. On to number 10. Write the formulas for compounds from the ions made of barium and sulfur. Barium is a group 2 metal. So these are all ionic compounds. Barium, group 2, is a 2 positive charge. Sulfur, we just went over this, group 16. It's 2 negative. Crisscross those, reduce. The formula unit is BAS for barium sulfide. Next one, lithium. Again, metal and non-metal. Lithium is in group 1. Has a 1 positive charge. Oxygen is group 16. It's going to gain 2 electrons, 2 negative. Crisscross those numbers down, and you get Li2O. Can't reduce that. There's your formula for lithium oxide. Next up, we have calcium and nitrogen. Calcium is a group 2 metal. It's going to form a 2 positive cation. Nitrogen is going to gain 3 electrons. It's going to be 3 negative anion. Crisscross those, and you're going to get Ca3N2 is the formula for calcium nitride. And copper 2 and iodine. Copper is Cu. Big C, little e. This is important. You don't write in all caps or all lowercase. You are definitely going to confuse others. And iodine is a halogen, 7 valence electrons, going to gain 1. Crisscross those numbers. So the formula unit for copper 2 iodide is CuI2. So like I said, this is going to get redundant pretty fast. So if you think you've mastered this, move on to the next section or scroll down to the end and you'll get more of a mixed review order. But let's keep going with these ionic compounds. Sodium is a group 1 metal, so it's going to form a 1 positive cation. Iodine is a group 17 non-metal, it's going to form a 1 negative anion. Crisscross those, you're going to get that 1-to-1 ratio, and the formula is going to be NiI. All right, B, stannous chloride. Okay, so our textbook that we use that I'm getting these problem sets from is more than 10 years old. So this is an older naming convention that you're not going to see on our test. But the way we used to name them is use their Latin root. So stannous is the Latin word for tin, and if it has an OUS, it's the lower charge of the. So this one. All right, so tin. So that also explains why tin is not T or TN or something. It's a lot of these metals have symbols based off their Latin name because English wasn't spoken when these things were discovered. And tin has 2 common charges, 2 positive and 4 positive. And so if it ends in OUS, that refers to the lower charge, and if it ends in IC, then it's the higher of the 2 charges. But you won't need to know that because all the problems on our test, and we'll have Roman numerals for you. So let's rewrite this the way you're more likely to see it. So this would be written on a test if you were to see it as tin 2 chloride. Okay, so let's go with that. So the symbol is still going to be SN. It's going to form a 2 positive charge, and then, chloride is chlorine, so that's going to be a 1 negative charge. Crisscross those numbers, and you're going to get a formula of SnCl2. And there's your formula for stannous chloride or tin 2 chloride. These are both the same thing. All right, potassium, group 1 metal. Write the symbol, write the charge, sulfur, symbol, and the charge of its most common stable ion. Crisscross those numbers, and your formula unit is going to be K2S. Okay. Let's see, let's go blue here. I've already done that. All right, calcium, group 2 metal, 2 positive cation. Iodine is, we just did that earlier. Crisscross those numbers. Can't reduce, so it's going to be CaI2. All right, I don't know what that is. Tin 2 fluoride and tin 4 oxide. Let's write the formulas. One's found in toothpaste and the other one's used in glazes for pottery. All right, let's do tin 2 is, we need a little bit more room than that. Let's go up here. The symbol for tin is capital S, lowercase n. Let's put the charge of the cation. Fluoride is fluorine, 1 negative. Crisscross those numbers. And the formula for stannous, tin 2 fluoride is SnF2. Now let's go to tin 4 oxide. That's going to have a 4 positive charge. We'll tell you the charges of all the transition metals that have multiple charges. Oxygen is 2 negative. Crisscross those, and you are going to get SN2O4. Now you got to reduce. These are ionic compounds. You got the metal and the non-metal, so our final answer is going to be SnO2. So now we're ready to name ionic compounds given the formulas. You just go right in the reverse order. Now you've got to be careful with these transition metals because a lot of these, like cobalt, can have multiple charges. So you'll have to go in reverse order to determine the charges. All right, so cobalt, right now, it's cobalt to iodine ratio is a 1 to 2. So that 2 Well, you know the charge on iodine is 1 negative, so that matches the 1 down there. So that means the 2 must have come from the charge on the cobalt, because cobalt can be a 2 or 3 positive in the most common cases. So the name of this one is going to be cobalt, and you've got to put the Roman numerals in the name. So cobalt 2, and it's not iodine, it's iodide. So make sure you rename those elements. The second element in these binary compounds, if it's an element, drop the ending and put an IDE at the end of that. So the name of that is cobalt 2 iodide. Now B, we don't need to do this reverse crisscross stuff because lithium is not a transition metal. It only has one charge. And when you only have one charge, you don't need to include it in the name. So it's just going to be the name of the metal, it's just in this case lithium, and then the name of the non-metal, which is selenium, but you've got to drop the ending and add IDE. So selenide is the name of Li2Se. All right, that's the only way they're going to, well, that's the most common way that they're going to form in that formula unit. Moving right along, naming some more ionic compounds. Zinc is a transition metal, but it only has one charge. So again, you don't need Roman numerals. You're just going to put the name of the metal, the zinc, and then the name of the nonmetal, sulfur, but change that ending to an IDE, so sulfide. All right, much easier when you're naming. So unless you've got transition metals with multiple charges. Again, here potassium can only have one charge, so the name here goes first. The metal is just the name of what it is, potassium, and chloride is not. I'm sorry, chlorine. You're going to have to change to chloride. So there's potassium. That's KCl. All right. Again, barium is can only have one charge, so no need for the Roman numerals. Just write the name of the metal, and then oxygen is change that name to oxide. Okay. Copper, now copper does have multiple charges, so these are where you have to kind of work it out in your head. Or so copper right now has a 1 next to the symbol, and bromine has a 2 next to it. These are not always going to be this simple. But for now, that 1 does match the 1 negative charge that bromine normally has. You normally want to start with the subscript on the transition metal, see if it matches the charge of the anion that it would normally have. And in this case, and so far, it's always matched, but it won't always, and that's when it gets a little tricky. All right, that means that too, the subscript from bromine must have come because the copper is a 2 positive charge. So this must be copper 2. So you got to know your Roman numerals up to at least 4. Bromine is going to be bromide. IDE ending. Let's keep going. Calcium. Just write the name. It just doesn't have more than one charge. Just write the name, and oxygen is oxide. There's CaO. All right, copper. Now, here's copper is a transition metal with multiple charges. So let's do this one. Copper has a 2 next to the subscript, and selenium has a 1 there. So again, start with the subscript of the transition metal and make sure that matches the normal charge of the anion. And again, it does. If it does, you can just use the subscript of the nonmetal, and that's going to be the charge of your transition metal. In this case, it's copper 1, selenide. All right, next one. Iron, again, is another transition metal that has multiple charges. So right now the subscript is 1, and the subscript next to sulfur is also 1. So using this subscript of the transition metal, you can see it doesn't match the normal charge of the sulfide anion. Sulfide normally has a 2 negative anion, so this must have been a 2 that was reduced to a 1. So that means the subscript of the sulfur was also a 2 reduced to a 1. So the charge of the iron cation must have been 2 positive. Again, if you're not sure, you can do a little trial and error and just check your answer. So for example, if you thought it was iron 1 positive, right, well, sulfur forms a 2 negative, and if you crisscross this, you get a formula unit of Fe2S, and that's not that doesn't match the problem, right? So you know this is going to be iron 2. When you have transition metals with multiple charges, you've got to put the Roman numerals in there in the name, and this is sulfide. Okay, aluminum can only form 1 charge, so these are the simple ones. You just write the name, aluminum, and then fluoride, and then fluoride. Okay. Example 3, lead 2 sulfate. Let's write the formula. All right, lead is Pb, Latin for plumbus, and the 2 tells you the charge on that cation is going to be 2 positive. All right, now sulfate is not sulfur. It's a polyatomic ion, and you should try to memorize that unless this is your last chemistry class you plan on taking. That's SO4, 2 negative, and so when you crisscross those charges, right, they're going to cancel out, and so your formula is going to be PbSO4. All right, shells of marine organisms composed of calcium carbonate. So carbonate is another polyatomic ion. It's CO3, 2 negative. All right, let's combine that with calcium, which forms a 2 positive cation. Those charges are going to cancel out, and your formula is going to be just CaCO3. Example number 5, lithium carbonate as medication. I'll let you read that. God looks very serious. All right, let's write the formula for lithium carbonate. Lithium is a group 1 metal. It's going to form a 1 positive charge. Carbonate is a polyatomic ion with a 2 negative charge. And let's crisscross these numbers, and 2 is going to go down there. That 1 doesn't matter, so it's going to be Li2CO3. More polyatomic ions. This is magnesium. It's just Mg. It's a second group 2 metal, so it's 2 positive charge. Hydroxide is OH1 negative, and so crisscross those. Now, if you have a subscript for a polyatomic that's not 1 or greater than 1, then you need parentheses, because watch what happens if I don't use parentheses. If I bring that 2 out there, that just looks like there's 2 hydrogens and 1 oxygen. Well, that's not correct. So you've got to put a parentheses around the polyatomic ion, put that 2 out there, because that's how we do that. All right, potassium sulfate. Potassium is symbol K. That's a 1 positive charge, and sulfate is SO4 with a 2 negative charge. Bring that 2 out there, bring that 1, it's not going to matter, 1s are not, so it's going to be K2SO4. Now, don't put parentheses if you only have 1 of those polyatomic ions. All right, ammonium is your positively charged polyatomic ion, 1 positive charge, and sulfite, remember, ite means 1 less oxygen, so it's not SO4, it's SO3. Same charge though, 2 negative. Crisscross those numbers. Remember, if you have more than 1 polyatomic ions, you're going to need parentheses. So that's NH4 parentheses, that 2 outside of that, and then since the sulfite is just 1 of them, you don't need parentheses for that. Here's your formula for ammonium sulfite. All right, next up, calcium is a group 2 metal, going to form a 2 positive cation. Phosphate is PO4. It's going to have a 3 negative charge on that. Crisscross those numbers. Now, again, polyatomic ions, you have multiple of them, you need parentheses. All right, that's Ca. Calcium's going to get a 3 as a subscript, and then we need parentheses. PO4, and then put a 2 out there. All right, now I've seen some people do this, like without parentheses. That's not, that's wrong. 42. Right? Don't do that. There it is. Calcium phosphate. Number 15. All right, lithium. That's Li. Hydrogen sulfate. Sulfate is SO4 with a 2 negative charge. Now when you add hydrogen to it, that polyatomic ion, that's like adding a proton. You're going to increase the charge by 1. So it's going to be HS, the hydrogen sulfate ion is going to have a 1 negative charge, right? Now lithium is going to have a 1 positive charge. Those charges are, those ones are going to cancel out, so your answer is simply LiHSO4. Chromium, charge is given to us, Cr, 3 positive. This is not an element. See, students always, do that very commonly. That's not correct. This is a polyatomic ion. Nitrate is NO3. Ite is 1 less oxygen. So chromium 3 positive. This is NO2. We drew Lewis structures, a lot of them. If you remember nitrite, the charge is still the same. It's 1 negative. Crisscross those charges. I'm sorry, crisscross those numbers, not the charges. And then you're going to get Cr, and then put parentheses there, NO2. And then that 3 goes outside that parentheses because you have 3 of those nitrites. Example 6, bleach. The compound NaClO is often added to bleach to brighten up the whites. So name the compound. Na is sodium. And all these halogens with oxygens, they're ClO3, they all have 1 negative charge, so it's kind of easier to remember. This is chlorate. If it's 2, it's chlorite. If you have 1 less than ite, you add hypo. Remember in biology, if you remember hypotonic and hypertonic, hypo means less concentration, if that helps. All right, anyway, this is the hypochlorite polyatomic ion, so sodium hypochlorite. All right, I feel like we're getting near the end of the section. Most students find the next section much easier when we're naming and writing formulas for molecular compounds. All right, but let's finish this off here. We are going to name this ionic compound. This is your ammonium. And this is oxalate. All right, next one. All right, so here's another example of a transition metal where you can have multiple charges. So that subscript next to iron, below iron, is a 1. So does that match the charge of the polyatomic ion? It does. So this is your chlorate polyatomic anion, and it does have a 1 negative charge. So that means the subscript outside of that, which is a 3, must match the charge of the transition metal. So this is going to be iron 3. Chlorate. And again, if you don't see that, you can do trial and error and try iron 1, iron 2, iron 3, iron 4, and then you'll see only iron 3 will give you the formula that the problem gives you. Number 16, here we go. Calcium is, that's what it is, an oxalate. Just write the name of the cation, and then if it's a polyatomic ion, then just write the name of that. If it's an element, switch the ending to IDE. All right, next up, that's K is potassium. And that's hypochlorite. Yeah, oftentimes naming can be pretty straightforward unless you have those transition metals. All right, let's keep going. K is potassium again. And MnO4, 1 negative, is your permanganate polyatomic ion. Okay, lithium and 1 less oxygen sulfate is sulfite, so that's lithium sulfite. Oh man, when's it going to end? 17, aluminum is Al, aluminum, OH is hydroxide, sodium, chlorate, tin. Oh, here's a transition metal with multiple charges. So here, all right. So that has a 3 on the subscript. Now, does that match the charge of the phosphate ion? The phosphate does have a 3 negative. So if that matches the charge of the anion, then the subscript, which is a 2, must be the charge of the cation. So it's tin 2 phosphate. Sorry. Okay, sodium chromate. Piece of cake. I'm sure we're getting close to the end here. We're writing formulas this time, so we need the charges. All right, beryllium, 2 positive. Chloride is chlorine, that's 1 negative. This is not. That's going to have a lot of covalent character, probably a much lower melting point. In any case, crisscross those numbers, and we get BeCl2. Cesium is group 1 metal, 1 positive sulfide. If it ends in IDE, that is a usually element that's going to have a 2 negative charge. Crisscross the 2, crisscross that 1, and it's going to be CS2S. Okay, sodium iodide. We just did this. I remember earlier on. There it is. 1 positive, 1 negative. Strontium is group 2. 2 positive. Oxide. Oxygen is group 16, 2 negative. Crisscross, and they're going to cancel out as well. Okay, I just peeked ahead. 26 is our last one. We're almost there, right? The formulas. So we're going to need the charges again. We're given the charges of we're given charges of transition metals with multiple charges. Just write the symbol. The charge is 3 positive. Nitrite, is that an element? No, that's a polyatomic ion. That's NO2 with a 1 negative charge. Crisscross. Now, when you have multiple polyatomic ions, you need parentheses. So that's CR, parentheses, NO2, parentheses, and then put that 3 outside there. Alright, sodium is Na, has a 1 positive charge. Think of hyper, means 1 more oxygen. So chlorate has 3 oxygens. Perchlorate has 1 more than that. So ClO4, charge is still going to be the same. Those ones are going to cancel out, and the formula is going to be NaClO4. Alright. Magnesium, hydrogen, carbonate, or bicarbonate. If you see that hydrogen, that's a proton, just increase that charge of the polyatomic ion. Let's start with magnesium. Magnesium has a 2 positive charge. Carbonate is CO3 with a 2 negative charge. When you add a proton, or bicarbonate, or hydrogen carbonate, we're going to increase that charge. It's going to be 1 negative now. So crisscross them, and so you're going to get Mg1. We don't write the 1. Now we need a parenthesis here because that 2 is going to say we have 2 of this bicarbonate ion. So HCO3, and then the 2 goes outside of that. Alright, calcium is your group 2 metal. 2 positive. Acetate is your CHO232, 1 negative charge. Crisscross those charges. You need a parenthesis around the acetate because there's 2 of them. C2H3O2, put a 2 there. Alright. Name the following compounds. That's Li is lithium, and F is fluorine, but don't forget to change that N to IDE. Tin, okay, again, you're going to need to get the charges here. So the way it's written here, that subscript on the transition metal, does it match? You know sulfide normally has a 2 negative charge, so that doesn't match. So that 1 must have been reduced. That 1 next to the transition metal must have been reduced from a 2. So that means the sulfur must have been reduced from a 4. Okay, in order to get a 1 to 2 ratio from it must have been 2 to 4. Right. If that doesn't follow, you can do some trial and error. It'll just take you a little bit longer. Just make sure you check your work and you get back what the problem states. All right. So that tin must have been a 4 positive charge. So it's going to be tin 4, and when we have sulfur is going to turn into sulfide. Here we go again. Manganese is another transition metal that can have multiple charges. So right now the way it's written has a 1 there, and does that match the charge of the carbonate ion? The carbonate ion has a 2 negative charge, so that 1 must have been reduced from a, what do you say? 2, right? So that must have been reduced from a 2. The subscript outside of this must have also been reduced from a 2. So it must have been manganese 2. All right, so let me go over here. Wait, what are we doing here? Writing names. Manganese 2. Sorry, that's parentheses, and then carbonate. All right, on the D, strontium. Let's write that. And this is dihydrogen, and that's phosphate. So you have dihydrogen phosphate, dihydrogen phosphite. So PO4 is phosphate. You got to memorize your polyatomic ions, unless we give you a reference sheet. Dihydrogen phosphate. Finally, last one. Which of the following formulas are incorrect? Okay. Let's just write it correctly, and then we'll see if it's incorrect. All right, so we got magnesium is going to have a 2 positive charge, and sulfate, SO4, is going to have a 2 negative charge. When you crisscross that, those charges are going to cancel out, so the answer is going to be MgSO4. So this is incorrect. Why? It's just wrong. I don't know what they're looking for. All right, B. So this is a new one. So when you're writing these, you should write the cations or the metals first, and the anions, the nonmetals, second. Cations first, anions second. I don't know who made this stuff up, but that's the rules we got to follow. All right, so rubidium is a group 1 metal. We're going to write that first. It has a 1 positive charge. Arsenic is right below nitrogen and phosphorus, so it can form a 3 negative charge, crisscross those, so the charges are right. Just the order is wrong. So it's going to be RB3AS. Okay, so that's just switched. All right, that one, the charges are wrong. Beryllium has a 2 positive charge. We just did this earlier, like 3 problems before this. So crisscross those, you're going to get BeCl2. So they're all wrong so far. This is correct. That one's right. Correct.